Hello! I'd like to start off this video by introducing you to what I like to call triangular constraint systems. A triangular constraint system looks something like this. So here we have a collection of triangles with letters up at the top and numbers down at the bottom, and then we have some partial triangles that are missing one of the numbers at the bottom. They form trapezoids, and they have octothorpes up at the top. So what we do with these triangular constraint systems, suppose we have a word on the letters that we have up at the top here. Step 1, we add octothorpes to both ends of the word, and then we draw a bunch of triangles and some trapezoids at the beginning and end. Our goal is to fill in numbers into these smaller triangles in such a way that every triangle and trapezoid at the end looks like one of these possible pieces. We don't have to use every piece, and we can use the same piece multiple times, but every single triangle and trapezoid has to look like one of these pieces. So let's go through and try to solve this. Well, in this first triangle here, we have two possibilities. We could either put a number 0 or a number 2. Let's say, for instance, that we put the number 2 here. And then we look at this triangle here. We see that a triangle that has on the left side a number 2 could wind up having a number 3 on the right side, or it could wind up having a number 1 on the right side. So we can either put a 3 or a 1 here, and we have to be careful about which we pick, and so on and so forth. And this might require trying out a sequence and then discovering that it doesn't work, and then we have to go back and try another possibility. It can sometimes be an interesting puzzle. Very often these things wind up being fairly straightforward. And they're not always solvable. It's not always going to be the case that this particular word has a sequence of numbers that we could put in here to satisfy the triangular constraint system. Every word that we can put in a sequence of numbers to satisfy the triangular constraint system is said to be a happy word with respect to the triangular constraint system, and every word that we can't fill in numbers in order to make every triangle and trapezoid look like one of our available pieces is said to be an unhappy word. So just like our finite state automata, these triangular constraint systems, when we have a particular set of trapezoids and triangles, we have a particular set of pieces, that's going to divide the set of words into the happy words and the unhappy words. In other words, it's going to define a language. We can use these triangular constraint systems to describe a set of words, the set of words that we can fill in numbers to satisfy the triangular constraint system. And so we might ask the question, what sorts of languages can we define by triangular constraint systems? Can we define every regular language by some specific triangular constraint system? That is, given a regular language, can we construct a set of pieces where that particular triangular constraint system only considers happy the words that are in that regular language? And vice versa, if we have the set of words which are happy with respect to a particular triangular constraint system, is that set of words regular? And it turns out the answer to these is both, and I'll show you why in this video. But to start out, try to fill out numbers into these triangles here in such a way as to satisfy this particular triangular constraint system. Or convince yourself that it's definitely the case that this task is impossible. Remember that for some triangular constraint systems, you're not going to accept all words. There's going to be sequences of characters here where you can't fill in numbers to make this constraint system satisfied. And if you want a little more practice with triangular constraint systems, I've linked an interactive below that will randomly generate you a word and a triangular constraint system to try to determine whether or not that word is accepted by that triangular constraint system. Whether or not there's a way of filling all of the numbers in order to make every single piece look like one of the available pieces. So let me spoil the answer for you. This is accepted by this particular triangular constraint system, and one possible sequence of numbers that we could fill in here is, as we can see, 0A1 is one of our possible pieces, 1B1 is one of our possible pieces, 1A2 is one of our possible pieces, and this piece actually gets used twice, and that's perfectly fine. And 2A1 is one of our possible pieces, and our left end piece and our right end piece are valid pieces here in this system as well. Now, there are multiple solutions to this problem, but that isn't such a big deal. We don't care about whether there's just one or multiple ways of filling in the numbers, and we don't particularly care too much what the way of filling the numbers in is. We just care about whether or not there is a way of filling in these numbers to make the triangular constraint system be satisfied. And again, that determines whether the triangular constraint system accepts or rejects the word, whether it considers the word to be happy or unhappy. So again, I encourage you to play around with these local constraint systems because I'm going to spoil how to solve them generally. So suppose that we want to determine if there is a solution, and if there is a solution, to find it. Well, what we can do is we can start at the left end triangle. We can also do this from right to left. That's perfectly fine as well. We start at the left end triangle and keep track of all of the numbers that we could write into that triangle. So in this case, because there's two left end pieces like this, we could write either the number 0 or the number 2 in this triangle here. Then this triangle here is a 0 or a 2 followed by an A. So what numbers could we write into this triangle? Well, if we have a 0 on the left, we could write a 1 on the right. And if we have a 2 on the left, we could either write a 3 on the right or a 1 on the right. And it doesn't matter. We don't have to keep track of the fact that there's two different ways of getting a 1 in this particular triangle. That's fine. We only have to keep track of which numbers we could write in this triangle. We then look at the next triangle. This is going to have a B up at the top, and it's going to have either a 1 or a 3 on the left. So what could go on the right? Well, if we have a 1, we can write a 0 or a 1 on the right, and if we have a 3, we could write a 0 on the right. Now we have an A that starts with a 0 or a 1, so it could be either a 1 or a 2. We have an A that starts with a 1 or a 2 on the left, so we can either have a 2, a 3, or a 1 on the right. We have an A that starts with a 1, a 2, or a 3 on the left, so on the right it could either have a 2, a 3, or a 1, and there's actually no way that it could have a 3 on the left because there's no A piece that has a 3 on the left. And then finally, we note that it is possible to fill in these triangles in a consistent fashion in a way that leads us to write a 2 in this particular triangle. And 2 is an acceptable thing to write in that triangle. So this means that there is, in fact, a solution to this problem. There is, in fact, a way of filling in these numbers to make this all work out. And remember that that's the important question. We don't care so much how to fill in the numbers, we just care whether or not you can fill in the numbers. But let's say that we actually did want to figure out how to fill in those numbers. Well, we can work our way backwards. Starting at this 2, what could have led to that 2? Which one of these possibilities? These are all possibilities that we can consistently reach working our way from the left. So which one of these possibilities could lead to a 2? Well, with an A, the only way to get to a 2 is through a 1. With an A, we can get to a 1 through either a 0 or a 2. But there's no way of getting a 0 in this particular triangle, right? We've listed out all of the possible numbers that could consistently, if we read this out from left to right, that could consistently be in this particular triangle here. And we can only write a 1 or a 2 in a way that's consistent on this part of the board. So we ignore this piece, and in order to get that 1, we need to use this piece. Now, how can we get a 2 with an A? Well, the only way to get a 2 with an A is with a 1. How can we get a 1 with a B? The only way to do that is with a 1. How can we get a 1 with an A? Well, there's two ways of doing this, either with a 0 or with a 2. So actually, either of these is a valid possibility for this particular triangle. And we can just arbitrarily pick one. We're looking for a solution, not all solutions. And the sequence of numbers that we see here, 0, 1, 1, 2, 1, 2, winds up being the solution that we're looking for this particular triangular constraint system problem. Now, here's the clever thing. Let's look at what we've actually done here. Between our inputs here, between the characters, we put a subset of the numbers from 0 to 3 according to certain rules. If we have a particular subset and we see a particular character, there's going to be a well-determined next subset to write. And that's simply, we look at the pieces and we say, what are the things that could follow a 0 and what are the things that could follow a 2? And then that determines what the next piece is. So knowing the set of numbers that we have on the left and the character that we read in determines the set of numbers that we write on the right. And the key thing here is that there's only a finite number of sets of numbers. There's a lot. We've gone from having 4 numbers to 2 to the 4th, 16 possible subsets down here, but that's fine. 16 is a finite number. So we have a finite number of things that we can write down here. We have a well-defined rule for going from one thing to the next, depending on what character we read. That is a transition function on a finite set of states. And we have a well-determined state set of numbers that we start off with. That's going to be just the set of numbers that can show up in these left-end pieces. And we have a well-defined criterion for when are we happy with a particular set of numbers here showing up at the end. Well, in this case, for this specific triangular constraint system, we're happy with a set of numbers that show up in the end. The triangular constraint system is going to be happy with the word that we've shown it if the state that we wind up in at the end has a 2 in it. And so we want to view these states, these subsets of the numbers from 0 to 3, as being accepting if they have a 2 in them. Or if we have a more general triangular constraint system, if they have at least one number that shows up in a right-end piece. So what this means is that for every triangular constraint system, we can construct an equivalent finite state automaton. And because of that, the set of words that are accepted by any triangular constraint system is going to be a regular language. In other words, triangular constraint systems are no more expressive than finite state automata, because there's nothing we can do with a triangular constraint system. There's no set of words that we can recognize with a particular triangular constraint system that can't also be recognized by the corresponding, we call this the power set automaton, because the states of this automaton are the power set of these numbers that are available. Every triangular constraint system can be translated into a corresponding power set automaton, and so the language of every triangular constraint system is going to be regular. Let's take a look at another triangular constraint system. I'd like you to take a moment to try to determine if this particular triangular constraint system accepts the word BABAAA. So again, remember, if you want to determine whether or not a particular triangular constraint system accepts a particular word, we add octothorpes onto the end, we sketch our triangles, and our goal is to fill in numbers down at the bottom so that every piece, including these end pieces, looks like one of the available pieces. You don't have to use every piece, and you can use the same piece twice. As we can see, this is a really boring triangular constraint system. There's only one possible number that we could put here, and then if we have a number on the left and a character, that's enough to determine what number goes here. So if we have a 0 and a b, we have no choices here. We must write a 0 here. If we have a 0 and an a, we must write a 1 here. If we have a 1 and a b, we must write a 1, and so on and so forth. And because this last number isn't a 1, somewhere along the line we have to break our rule. We have to break our constraints. So there's no way of filling in numbers so that all of the triangles and the trapezoids on the left and the right look like the available pieces. This word, BABAAA, is not part of the language defined by this particular triangular constraint system. Now, what I've done here is I've secretly taken the finite state automaton from our finite state automaton video that recognizes the language of words that only have an odd number of A's and no C's in them, and converted it into a triangular constraint system. If we wanted to, we could view each of these numbers here as a state of our deterministic finite automaton. We start off in state 0 before we read our first character, and this is enforced by having just one piece that looks like this, and then after we read that first character, we have to wind up in state 0, and that's enforced by the fact that there is exactly one piece that goes 0b something, and that something is the thing that we would transition to in our finite state automaton after reading the character b starting in state 0. And so these numbers here are the sequence of states that we would wind up in if we ran this particular word through our deterministic finite state automaton. And then the only thing that we're checking is whether or not the state at the end, after reading the last character, happens to be one of the acceptable final states. Here we only have one right end piece because the original deterministic finite state automaton only had one accept state. So generalizing this technique, we are able to turn every deterministic finite state automaton into a corresponding triangular constraint system. These triangular constraint systems that we get are going to be very limited. They're only going to have one left end piece and be very restricted as to what sorts of triangles we can have, but that's still a valid translation. We'll be translating our finite state automata into corresponding triangular constraint systems. What this means is that for every regular language, right, that comes from a finite state automaton, we can take that finite state automaton, translate it into a triangular constraint system, and thereby have a triangular constraint system that recognizes exactly that regular language. This particular triangular constraint system recognizes exactly the language, exactly those words which have an odd number of A's and no C's in them. Every deterministic finite automaton can be translated into an equivalent triangular constraint system, and every triangular constraint system can be translated into an equivalent deterministic finite state automaton. In other words, the set of languages recognized by some triangular constraint system is exactly the regular languages. This is an equivalent categorization of the regular languages. Now, seeing the way that we can translate deterministic finite state automata into triangular constraint systems, and seeing these extra constraints that are on the deterministic finite state automata that we get when we do that translation, in other words, seeing the ways in which triangular constraint systems are less constrained than deterministic finite state automata, gives us some ideas for how we could generalize the notion of a finite state automaton. In particular, triangular constraint systems can have as many left-end pieces as they want. And these left-end pieces correspond to the start states of our finite state automata. So this inspires us to make the generalization that we should allow our finite state automata to have potentially multiple start states. Now, what does this mean? This means that we might not necessarily have a unique sequence of states that corresponds to any particular word input. We might have a different sequence of states if we start off somewhere different that still winds up accepting. And the idea that comes out of the triangular constraint system is that we only care if there's one sequence of states that makes everything work, that starts the way we want it to, that transitions the way that we want it to, and ends the way that we want it to. If there is at least one way of filling in these numbers, filling in these states, that makes this transition relation work, and the start state work, and the end state work, then we say that the word is accepted. And so that's going to be the generalization that we want to use in constructing this new type of finite state automaton. So our second way that we're going to want to loosen the restrictions on deterministic finite state automata is allow it to be the case that if we are in a particular state and we see a particular character, we might have multiple states that we could wind up in next. This is what's allowed with triangular constraint systems, and remember, again, with triangular constraint systems, it simply has to be the case that there is some sequence of states that will allow you to get from the start to the end, satisfying the transition relation. So if you can come up with one of any of a number of paths that works, as long as there's one, then we're happy. And finally, the last generalization that we can make is that we might want to remove the possibility that we can do anything if we're in a particular state and we see a particular character. Suppose we're in state 2 and we see the character C, and this piece is gone. We've removed this piece from the triangular constraint system. This is not something that you can do with a deterministic finite state automaton. With a deterministic finite state automaton, it has to be the case that if you're in state 2 and you read the character C, you have to wind up in some state. But with our generalization corresponding to triangular constraint systems, we can remove that possibility. We can say if you are in state 2 and you read the character C, you're sunk. You have to backtrack and try a different path, try a different sequence of states, different choices earlier on, in order to try to get you to the end, and if you can't find one, then you reject. Then this word is not accepted by this particular triangular constraint system. These generalized versions of deterministic finite state automata are called non-deterministic finite state automata. So just like with deterministic finite state automata, we're going to want to have a finite alphabet and call it sigma, and a finite set of states and call it capital Q. The difference starts where we have now a set of start states. And then, instead of having a transition function, we have a transition relation, where we say that delta of state 1, some character, and state 2, if we can transition from state 1 to state 2 when we read the character C. We don't have to. There might be other states that we can transition to, but this is one of the possible transitions that we can make. This relation corresponds to what pieces are available in our triangular constraint system. The more pieces, the more triples satisfy this particular relation. And it could even be the case that every triple satisfies this particular relation, in which case we have a great deal of flexibility as to how we want to go from the start to the end. And finally, we have our set of final states. And again, the rule is that our non-deterministic finite state automaton accepts a particular word if there is some sequence of states that starts where we want it to, has valid transitions, that is, that the state before reading a particular character and then the state after we read that particular character has to satisfy this transition relation, and our sequence of states also has to end in one of our set of final states. In this case, we say that our sequence of states respects our start state, our transition relation, and our set of final states. This sequence of states is very important for analyzing the behavior of both deterministic and non-deterministic finite state automata, and so we give this sequence of states a special name. We call it a run. And we can view this sequence of states as a sequence of elements of some finite collection. Not our finite alphabet, but our finite set of states. And so we can view these runs as words with a slightly different alphabet. And that will turn out to be an extremely important perspective on finite state automata in a later video. Let's take a look back at our original triangular constraint system. Here, according to our analogy, we're looking for a sequence of states where the first state is one of these numbers, one of the possible start states, and it can be either one. We're looking for each set of state and then character that we read and then state after we read that character to belong to one of these triangles. In other words, to be satisfied by the transition relation. And there may be multiple ways of doing that, multiple ways of filling in the numbers in order to get the transition relation to be satisfied. But as long as there's one way of filling in the numbers, then we're happy. So just as we can represent particular deterministic finite state automata as graphs, we can also represent non-deterministic finite state automata as similar graphs, but with fewer restrictions. Let's translate this particular local constraint system into a non-deterministic finite state automaton and look at what its graph looks like. So here we're going to have 4 states, 4 numbers here, 0, 1, 2, and 3. There's actually multiple start states. We could start off in state 0 or state 2. So we'll indicate that with 2 arrows coming in from the outside world. If we're in state 0 and we see the character A, we could transition into state 1. If we're in state 1 and we see an A, we could transition to state 2. If we're in state 2 and we see an A, we could transition either into state 3 or state 1. So here we see that we've lost the constraint that every state has exactly 1 arrow coming out of it with each particular character. We've also lost the constraint here at state 3 in the fact that if we're in state 3 and we see the character A, there's no state that we could transition to. There's no arrow labeled A leaving state 3. In that case, the automaton fails, and we just need to try another path. We need to go back and try a different sequence of states, a different sequence of choices, to see if we can satisfy the transition relation. And then for B, and finally, our set of final states, our set of accept states, are determined by these right-end pieces. And there's only one available here, and that's 2. So this here is our state diagram for the non-deterministic finite state automaton corresponding to this triangular constraint system. So that's it for this video. I hope you learned something, and I hope to see you in a future video.